We welcome you all to our presentation at this RISC-V Summit 2021 on the topic titled A Posit Arithmetic Enabled RISC-V Processor. We are from the Secure Hardware and VLSI Design Group at the Center for Development of Advanced Computing, CDAC, Bangalore, India. I'm Vivian with my colleague Aneesh. We both will be presenting this work. The agenda of the talk is as follows. To begin with, highlights of our work will be presented. A brief introduction to Posit number system will be presented, and the recent times arithmetic will be compared with IEEE 754 2008 floating point. The core of the presentation will focus on our hardware Posit Arithmetic Unit with Quire for RISC-V processor. The Posit unit has been architected suitably to be compliant with RISC-V F and D extensions. Further, the microarchitecture of the two versions of IEEE 754 2008 FPU compliant with RISC-V ISA F and D extensions, FPU High Performance and FPU Lite that had been developed will be presented. Subsequently, the architectural details of our 6-stage RISC-V processor with Posit Arithmetic Unit will be presented. The processor can have either Posit Unit or IEEE 754 2008 FP unit. It's imperative that a Posit Arithmetic Unit enabled RISC-V processor will require software toolchain modifications, and details about how the toolchain modifications will be also presented. Finally, few sets of results and analysis thereof will be presented in detail before concluding this talk. The highlights of our work include the following: P16, P32, P64, and Quire supported Posit unit, IEEE 754 FPU supporting single and double precision, our RV64 IMAFD processor, RISC-V processor and SoC Posit or IEEE 754 unit for floating point computations, RISC-V software toolchain modifications to support Posit arithmetic based computations in applications, evaluation and accuracy analysis of core with Posit unit and core with IEEE 754 unit with various computation kernels like cos x, square root, e power x, algorithmic estimation of pi value. Y-Cruncher has been the reference for pi. 128-bit float-based computations is the reference for the rest of the computation kernels. And lastly, the hardware resource complexity and performance analysis. As we begin, Posit number system has been captured in brief here. It was introduced in 2017 as an alternative for IEEE 754 floating point numbers, and has indicated several advantages over IEEE 754. In the Posit number representation, both the exponent and the fraction bit position and width varies, and there is a new field called regime. The general notation is Posit n, es, where n is the bit width and es is the exponent bits max width. The es field can be varied to trade off between dynamic range and precision. Sign bit 0 indicates it's a positive number and 1 indicates it is a negative number. Regime bits are what is unique to Posit. It is not present in floating point format. It is what provides tapered accuracy. That is, there is a decreased accuracy for larger numbers and increased accuracy for smaller numbers. It is used to calculate the scale factor UC raised to k, where UC is 2 raised to es, and k is determined by the number of identical bits terminated with an opposite bit, as can be seen in the figure. This field can extend from minimum 2 bits all the way to the entire bit field, in which case the exponent and the fraction bits will disappear. Exponent bits represents the scaling factor 2 raised to e, and fraction bits are preceded by an implied hidden bit, which is always 1. A brief comparison of Posit and IEEE 754 is presented here. Floats have more data representations such as normals, subnormals, plus or minus 0, plus or minus infinity, and nans. Posits have fewer formats, normal, NAR, and 0. Posit produces bitwise identical results across systems. The representable values using Posit format are always higher than using floats for the same number of bits. There are no subnormal numbers in Posit. The hidden bit is always 1. There is only 1 0 and 1 NAR representation in Posit. Bit patterns are identical in Posit if checked for equality. This is not the case with floats, since minus 0 equals to plus 0. In POSIT, two NARs are equal, while in float, two NANs with similar bit patterns are unequal. There are no overflow and underflow issues in POSIT. There are fewer exception scenarios in POSIT, which results in simpler hardware. There is only one rounding mode, while there are 5 in 754 format. With this introductory note, I'm handing over to my colleague Aneesh Raveendran to continue with the rest of the talk.
Our Posit Arithmetic Unit is suitably designed to utilize RISC-V ISA F&D extensions for single and double precision and was developed in Verilog HTL. The hardware realization is fully compliant with the Posit arithmetic specifications. A single hardware Posit arithmetic unit can handle 16, 32, 64-bit Posit numbers, and it's a fused unit for various data bits and can perform 96 RISC-V floating point operations in Posit. As indicated in the POSIT specification, our hardware unit has adopted only round ties to even. Considering the newly introduced data representation and the corresponding arithmetic, verification of RTL code for POSIT unit is a challenge, and meeting the recommended code coverage metric. Multiple verification strategies and methodologies have been adopted, like using randomly generated set of test vectors for input operands, converting IBM FPGen test vectors into POSIT test vectors, converting Berkeley test float vectors into POSIT test vectors, and PositGen, an in-house developed test vector generator for verifying POSIT arithmetic based computations. Regarding PositGen, more details can be found out from our publications reference 9. As known to all, verification of any arithmetic unit needs a reference. In our case, soft POSIT has been adopted as the reference for 32-bit POSIT and Universal Stillwater Library for 64-bit POSIT. Using the mentioned test vector generation methodologies, all our computational units have been verified. We have performed code coverage analysis as well, and we could reach an average of 93 to 95% various code coverage matrices like toggle coverage, FSM, FEC, etc. As mentioned earlier, our Posit arithmetic unit supports Quire-based computations with a dot product engine. Posit unit with Quire for a RISC-V processor has been realized with 8 independent computational units with a balanced number of pipeline stages, except fused addition square root unit, which is an iterative hardware realization. Fused multiple accumulate unit caters to addition, subtraction, and multiplication. Our Posit arithmetic unit is pluggable into RISC-V processor pipeline. The front-end interface of the POSIT unit accepts maximum of 3 operands along with the RISC-V FP instructions. Instruction decoder at the input stage of the POSIT unit decodes the instruction and enables the respective computational unit. An instruction identifier for the dispatched instruction to the computational unit is kept in scheduler FIFO. Once the computation ends, the results are stored in result FIFO. And as per the instruction order in the scheduler FIFO, results are read out from the result FIFO and sent to the next stage in the processor pipeline. Basically, our POSIT arithmetic unit as an independent entity is an out-of-order dispatch, execute, and an in-order commit engine. More details of the internal microarchitecture on fused multiply accumulate and fused division square root, which are the key computational units in POSIT arithmetic unit, can be obtained from our publications references 7 to 9. Just to illustrate as part of this talk, the internal microarchitecture of two major computational units are shown here. Multiply accumulate has a latency of 6 clock cycle, and division square root, which is an iterative operation which takes 30 clock cycle for 32-bit POSIT and the 61 clock cycle for 64-bit POSIT computations. Now, moving on to the next topic on our IEEE 754 2008 floating point unit for a RISC-V processor. Two variants had been developed, one targeting high-performance applications with a deep pipeline, non-fused and independent computational units called FPU High Performance FPHP. And the second one, area optimized, targeted for low area, low power applications with a shallow pipeline and fused computational units called FPU Lite. Both variants have been developed using BlueSpec system Verilog. FPU variants are compliant with the IEEE 754-2008 specifications and adhere to all the specified number formats, rounding modes, and exception handling mechanisms. The FPUs are pluggable into RISC-V processor pipeline. The FPU high performance core illustrated in this figure along with its block level architecture and latencies of independent computational units. It comprises of 13 compute engines that performs 55 floating point single and double precision operations. The FPU has a front-end interface for taking maximum of 3 operands along with a RISC-V FP instruction. The input decoder decodes the instruction and dispatches the operand to the respective computational unit. Similar to the POSIT unit, an instruction identifier is kept in scheduler FIFO for each dispatched instruction. Output decoder reads the sequence of instruction identifier from the scheduler FIFO, reads the output from the corresponding functional unit, and dispatches the output to the next stage of the RISC-V processor pipeline. The output has a 64-bit data, 5 exceptions, and a single bit to indicate whether the output is a single precision or double precision data. Fundamentally, as similar to POSIT unit, the high performance FPU is an out of order execute and an in order commit engine. More details about our FPU variants can be obtained from our publication references 1, 2, 4, and 5. As mentioned, FPU Lite has been designed with the area optimization and it is meant for low area and low power applications. The computational units are fused for hardware reuse to minimize the area. It handles 58 RISC-V single and double precision floating point operations. It has fused multiply accumulate and fused iterative division square root units. Computational units adopts balanced pipelines to have a closely uniform latencies across the computational entities. The internal algorithm for various computations are similar to that of FPU high performance. To illustrate the block level architecture of FPU Lite and the latencies of each computational units are presented in this slide. Fundamentally, as similar to our POSIT unit, FPU Lite is an out of order, execute and in order commit engine. As the next agenda of our talk, a brief overview of developed 64-bit single issue in-order 6-stage pipelined RV64 IMAFD processor core will be presented. The core is compliant with the RISC-V user level specification 2.2 and privilege level specification 1.10. It supports two privilege modes, machine and user. Further, it supports exceptions and interrupts. The core has a branch predictor and a hardware integer division and multiplication unit and other various CSRs. The core has been verified using RISC-V compliance suite, RISC-V DB, AAPG, CSmith, and various standard workload programs. The core boots FreeRTOS and it is primarily targeted for embedded system kind of applications. The major pipeline stages are fetch, decode, register select, execute, memory access, and write back. Our POSIT unit and FPU Lite that earlier we have presented has been integrated with the processor core as a functional unit in execute stage. As mentioned, either POSIT or IEEE 754 for FPU can be made functional in the processor core, means processor core pipeline, and both cannot coexist or co-work together. The core with the POSIT unit and core with IEEE 754 for FPU have been evaluated separately and the same set of computational applications and kernels were run on POSIT based RISC-V core and 754 unit IEEE 754 based RISC-V core. The results were compared and presented in the upcoming slides. The processor core with either POSIT or 754 FPU as the base platform for our RISC-V SoC and this slide illustrates its overall architecture. The in-house developed peripherals, static memory controller, eMMC controller, watchdog timer, PWM, GPIO and QSP has been integrated with the processor core. The boot ROM in the SoC initializes the above mentioned peripherals. The 32 KB non-blocking level 1 instruction and data cache controllers also has been integrated with the processor core and the AXI interconnect. The core has a PLIC to support external interrupt and it has a CLIN to support the timer interrupts. The binary image applications are loaded into the SRAM which are used to execute various computational kernels to evaluate POSIT and IEEE 754 FPU arithmetic unit enabled RISC-V processor cores. The printf in the functions are redirected to the UART port for displaying the messages in the host machine. This SOC environment has been used as an integrated platform for evaluating POSIT RISC-V core versus IEEE 754 2008 FPU RISC-V core. The SOC has been prototyped on Xilinx Vertex UltraScale VCU 108 FPGA based board to validate the functionality on hardware. The SOC boots FreeRTOS and runs applications. The Quire, as part of POSIT specification, enables the accumulation of multiple computations, typically multiplications with a higher precision. The Quire accumulation is part of multiple accumulate, where the accumulation happens in a fixed point or wider precision register. This enables higher precision computation of all fused multiple accumulate instructions. The dedicated dot product engine computes the product of two POSIT numbers, and the result of the dot product is accumulated as Quire in a fixed point wider precision register. This engine is accessed with a custom instruction which will be useful for matrix computations with a higher precision. The Quire register size is dependent on the square of maximum POSIT value and the square of minimum POSIT value. For n and es POSIT number, the Quire register size is computed as per mentioned in the equation in the slide. I represents the maximum number of iterative computations that can be accumulated without losing the accuracy. The dot product engine supports P16, P32 and P64 data representations based on POSIT operands. These instructions for each data representation amounts to total 9 instructions as illustrated in the slides. The major 3 instructions are accumulate Quire, which multiplies two POSIT numbers and accumulate the product as Quire in a wider register. Clear Quire initializes the Quire register with 0. Read Quire reads the value from fixed point wider precision register, converts it into respective POSIT 16, 32 or 64-bit value. RISC-V floating point ISA has been extended with a set of additional function 5 func5 values to support new custom Quire instructions for P16, P32 and P64. For hardware realization of dot product engine with Quire accumulator, the accumulator size is defined as 1998 for equal to 64-bit and has a pipeline latency of 10 clock cycles. The dot product engine is fused to support P16, P32 and P64 based Quire operations. The dot product engine is verified at a test bench level using test vectors. Architectural optimization of the dot product engine with the Quire, integration with the processor core and evaluation using workload programs, say linear algebra operations, are under progress. RISC-V processor with a Posit unit instead of FPU needs software toolchain enhancement to handle Posit data representation. RISC-V GCC toolchain has been enhanced such that instead of IEEE 754 single and double precision data representation, the compiler incorporates Posit 32,2 and Posit 64,3 data representation. RISC-V GCC's internal real value type intermediate format was modified to generate P32 and P64 data representation to support POSIT-based computation in our RISC-V processor. Currently, ES values of only 2 and 3 are enabled and we are working on enabling the compiler flags to pass ES as values. Further, since our Posit unit is enabled with the RISC-V processor which has a dot product engine with the Quire, the RISC-V toolchain also has to be enabled or modified to support the custom instructions. So for that, RISC-V binutil assembler has been modified to support new POSIT Quire related custom instructions for dot product and accumulation. Inline assembly has to be used in applications for accessing POSIT dot product engine custom Quire instructions. RISC-V toolchain enhancement for POSIT data representation and POSIT dot product engine with the Quire have been illustrated in this slide. Firstly, for computation in POSIT, in the C program, 3 float and 3 double variables have been declared and defined. The corresponding assembly codes are shown. It indicates that the numbers have been inferred as POSIT representation and not as IEEE 754 data representation. Secondly, the binutil assembler modifications for custom instructions are shown in the right side of the slide. These custom instructions for Quire dot product engine are to be used in the C program by using inline assembly. The illustration shows a C program which computes the dot product of matrices. For the computation, we have used POSIT Quire POSIT Quire with clear, accumulate, and read in the inline assembly sequence. The figure on the far right side shows the Quire custom instructions are being inferred in the assembly program. This slide illustrates the latency, area, and maximum frequency of FPU and POSIT arithmetic units. We used Xilinx UltraScale VCU 108 FPGA development board to perform hardware validation and analysis of area frequency for both FPU and POSIT units. POSIT and FPU units as a standalone, we are validated independently on VCU 108 FPGA development board using PCI interface with the POSIT and FPU test vectors sent from host machine. In terms of latency, both FPU Lite and POSIT have similar clock cycles. FPU Lite, developed using BlueSpec System Verilog, was able to achieve a frequency of 153 MHz. POSIT unit, developed using Verilog HDL, achieved a frequency of 164 MHz, showing a marginal improvement over FPU Lite. In terms of hardware area, we noticed that POSIT arithmetic unit had lesser LUTs and registers. This slide depicts the number of decimal digits that are matching for FPU versus POSIT arithmetic units while running pi estimation and cosine value computation using Taylor series. Y-Cringer has been the reference for pi estimation and 128-bit float-based computation is the reference for the rest of the computational kernel. The matching decimal digit with respect to the references are indicated in green color. For pi estimation, we can observe that POSIT 32,2 and FPU SP are having identical number of matching decimal digits, while POSIT 64,3 is having one extra decimal digit matching than FPU DP was observed. For cosine computation, we are using Taylor series. We observed that POSIT has more number of matching decimal digit for both 32,2 and 64,3 calculations. This slide depicts the number of decimal digits that are matching for FPU versus POSIT arithmetic unit while running square root computations using Newton-Raphson method. The matching decimal digit with respect to the reference are indicated in green color. This slide depicts the number of decimal digits that are matching for FPU versus POSIT arithmetic unit while computing e power x using Taylor series. The matching decimal digits with respect to the reference are indicated in green color. This slide illustrates the graphical representation of e power x using Taylor series for FPU SP versus POSIT 32,2 and FPU DP versus POSIT 64,3. We notice that as the value of x increases, the matching decimal digits for POSIT decreases, while FPU maintains constant matching of decimal digits. We are currently evaluating both POSIT and FPU for other computational kernels as well. These are our publications and some of the references for our work. Publication 1 to 9 are our research work published in various international conferences in the area of FPU architecture, POSIT algorithms, POSIT architecture, and RISC-V processor core design. To conclude our work, we have designed a hardware POSIT arithmetic unit with Quire and IEEE 754 2008 compliant FPU high performance and FPU Lite arithmetic units for our RISC-V processor. The POSIT unit has been architected suitably to be compliant with the RISC-V F&D extensions. POSIT and FPU arithmetic units were integrated with a 6-stage in-order RV64 IMAFD RISC-V processor pipeline. Core enabled with the FPU or POSIT, level 1 instruction and data cache, and peripherals were integrated to form a SoC framework. RISC-V GCC toolchain had been enhanced for compiler to incorporate POSIT 32,2 and POSIT 64,3 data representation. RISC-V binutil assembler modified to support new POSIT Quire custom instructions for dot product engine. RISC-V core with the POSIT unit and core with the IEEE 754 FPU have been evaluated separately. The same set of computational application kernels were run on POSIT based core and IEEE 754 FPU based core. Results were evaluated and analyzed for hardware area and latency. Also, results were evaluated and analyzed for matching number of decimal digits for FPU versus POSIT. The following are the team members who contributed towards this work. This concludes our presentation. Thank you for listening to our talk.